Hey Precap, so today we were talking about complex numbers, and to start with, let's talk a little bit about the impetus for where complex numbers comes from. So if I was looking at this from x squared plus 4, lately we've been doing a lot of factoring and a lot of talk about polynomials, and we've noticed that the degree of the polynomial would tell us that there should be two solutions to this problem. And solutions come in the form of x-intercepts, usually if we're graphing. And so, following this logic, if we were to graph this guy here is a parabola and it's been shifted up 4 units. So if I were going to go ahead and draw a sketch of my graph, I would go up 4 units, so 1, 2, 3, 4, I'll call that 4. There's my 0, 0, like if I plugged in 0, 0 squared is 0, plus 4 is 4. If I plugged in 1, 1 squared is 1, plus 4 is 5. So I'm going to call this over 1. And negative 1 squared is 1 plus 4 is 5. And if I plugged in 2, let's see, 2 squared is 4 plus 4 is 8. So, and here's my parabola shifted up 4 units. Now the problem with this is it doesn't have any x-intercepts, but we've been seeing that the degree always tells us the number of solutions. And so this would look like a problem that has no solutions. For a long, long time, it was just accepted that it was no solutions, but then we started having problems where we're like, no, we want an answer to this. And so if you follow algebraically, you have x squared plus 4 equals 0. You could take 4 away from both sides. You would get x squared equals negative 4. And when you square root both sides, now I know if you do this on your calculator, it'll say no real solutions, and that's because this is actually an imaginary solution. You're going to break this apart as the square root of 4 times the square root of negative 1. And by the way, we need to remember our plus and minus. And here, the square root of 4 is 2. Well, mathematicians got kind of annoyed with writing the square root of negative 1 over and over. It was actually Euler, spelled E-U-L-E-R, pronounced Euler. He's a famous mathematician. He's responsible for all sorts of things. We'll talk about him more this year. But one of the things that he gave us was he standardized the use of I for the square root of negative 1. And so because he was so famous and he used it so much, that shortcut of using I for the square root of negative 1, we still use it today. Now, what this means is whenever you see an I in a problem, this is really standing in for the square root of negative 1. So for instance, on this problem, if I were to simplify, well, it's multiplication between the two parentheses. So what I think I should probably do is FOIL. 3 times 4 gives me 12. 3 times negative 2i gives me negative 6i. 5 times 4 gives me 20i. And 5i times negative 2i is a negative 10i squared. So now I can combine some like terms here. I have 12, a minus 6, and a plus 20 is a plus 14i. And I squared, since I is equal to the square root of negative 1, if I square it, I squared is equal to negative 1. And so instead of I squared, I can write a minus 1 here. Negative 10 times negative 1 is a plus 10. So 12 plus 14i plus 10. And then 12 plus 10 gives me 22 plus 14i. Now in a problem like this, the 22 is the real part, and the 14i is the imaginary part. And together, these two pieces are called a complex number. So moving on mathematically, if we're going to keep simplifying here, let's see, on this problem I have subtraction, which means I want to take this binomial and subtract the second one. So I'm going to distribute the negative. That gives me 6 plus I minus 7 minus 2i. And when I combine like terms, 6 minus 7 is negative 1. I minus 2i is minus 1i, or you could just say minus I. Go ahead and box that since that's my final answer. And again here, the negative 1 is the real part, and the negative 1i is the imaginary part. Now, you might see problems like I to the 23rd. We saw some different ways of dealing with this today. One way that was nice that I'm going to show you in the notes is to think of this as I squareds. So if I wanted to write this out as I squared times I squared is I to the 4th, times another I squared would be I to the 6th, and I would have to write this out whole bunch of I squareds. Well, let's see. 2 goes into 23 11 times. And then to get, that would be I to the 22nd, right? That's like I to the 22nd. And then I would have to multiply it by I to get I to the 23rd. So I'd have 11 I squareds, and then I'd have an extra I on there. Well, since this is an odd number, that means that I'm going to have -1 times -1 times -1 an odd number of times. So that's like saying I squared to the 11th power times I. Well, I squared is a -1 to the 11th times I. And then a negative number to an odd power stays negative, so this would be -I. That's one way you could do this problem. Obviously there are others, but that's one way that'll work every time. And the only thing you have to remember in this case is that I squared is -1. Okay. For part D, if you see a division problem with i's, we're going to multiply by the conjugate. It's a little piece of vocabulary for you. Conjugate. Okay. So I'm going to multiply by 1 plus 2i on top and on bottom. It's a difference of squares on the bottom. So when I FOIL, I'm going to get, let's see, where do I have space? I'm going to come down. 3 times 1 is 3. 3 times 2i is 6i. 5 times 1 is 5i. 5i times 2i is 10i squared. On the bottom I have a difference of squares, so 1 minus 4i squared. And now I can combine like terms and plug in -1 for I. So let's see, I get 3 plus 11i. Plus 10i squared is going to become a minus 10 because I squared is -1. And then on bottom I have 1, and let's see, I squared is -1, so that'll make it a plus 4. Now when I combine like terms a little bit farther, 3 take away 10 is -7, 11i over 5. And now technically what I should do to write this as a real part and imaginary part is break it into 2 pieces. So my final answer here would be -7 over 5 plus 11 over 5i. So the first part is my real part and the second part is my imaginary part. We didn't do this today in class, so will you please make note of this and maybe I should go back and change your homework problems. The last 2 examples, we have another division problem. We saw today in class that you could multiply by the conjugate. So you could do -4i on top and on bottom. You could also make your life easier, however, by just multiplying by I. Really all we need is to get an I squared on the bottom so that it cancels out and turns into a -1. So in this case, I would get 7i plus 3i squared over 4i squared. And then the I squareds would turn into -1s, so this would become -3 plus 7i. And this would become a -4 on bottom, so I'm going to break this up and put both over -4. And when I do that, I see I have a negative over a negative is a positive 3/4 minus 7 over 4i. And notice here I'm putting the I beside the -7/4 instead of putting it on top. Go ahead and do that also, please. It's just kind of a formatting thing. It's just standard practice. It wouldn't be wrong to say 7i over 4. It just wouldn't look right like in the back of your textbook. And last but not least, on a problem like this where you see the square root of -1/3 and the square root of -27, you need to poke out the eyes. And when I think of this, I always think of the Three Stooges where they poke each other's eyes out. So here I'm going to poke out an I, so this would be I root 1/3 and I root 27. And now you can multiply your i's together, so I times I is I squared. 1/3 times 27 is the square root of 9, and the square root of 9 is 3. So this would be -3, since I squared is -1. Notice, had you multiplied them together in the beginning, a negative times a negative would have made a positive, right? And that would have been the positive square root of 9, and you would have got +3 for your answer. So you have to poke out the i's in the beginning to get the right answer in the end. Alright guys, that's it for notes for tonight. Please make sure you get these written down, and we will check them off tomorrow in class. Thanks. Have a good night.